I'm going to be talking about models with two-dimensional space and plus one-dimensional time. So these are our coarsening models. Here's a list of various collaborators on various things I'll talk about and some things related to them that I actually won't talk about. The two underlying names are students, one graduate student, Federico Camilla, undergraduate student, Elizabeth Zollinger, who may be either looking for postdocs or graduate student positions in a year. Or, so that's why their names are underlined. Coarsening is a much studied in the physics literature simple model of domain formation. I will primarily talk about it on either Z2, the square lattice, or the hexagonal lattice. When I get to the hexagonal lattice, I should hopefully remember to explain how I'm looking at it, so to avoid confusion. Coarsening corresponds to the zero temperature limit of Glauber dynamics, which is single spin flip stochastic dynamics for easing models, which leaves a Gibbs distribution invariant. But if that doesn't mean anything to you, it doesn't matter, because I'm going to define it directly. It's an extremely simple model. It's very much like majority vote models for interacting particle systems. It's a continuous time Markov process. The states are assignments of +1 or -1 to the lattice. At random times, which means times chosen at each site by a rate 1 Poisson process independently for the different sites, the site looks at its neighbors in the lattice and tries to agree with the majority. So it either stays as it was if it already agrees with the majority, or it flips, changes its value if it did not agree with the majority. And in a lattice like Z2, where there are 4 neighbors, if there's a tie, 2 plus neighbors and 2 minus neighbors, then it tosses a fair coin to decide what value to take.
You said that it was like the voter model.
No, I said it was like the majority vote model.
Like the majority vote model. How is it in any way different?
Oh, I think people who do majority vote models in particle systems, maybe somebody can correct me, often take a different rule when there's a tie. And in fact, it's crucial that one takes the rule that when there's a tie, 2 plus and 2 minus, you toss a coin, rather than, for example, the conservative rule of not changing. That would actually dramatically change the dynamics in, say, the square lattice, or the asymptotics. And this is what you get when you take ordinary Glauber or heat bath dynamics and take the limit as temperature goes to 0. Okay, the only remaining thing to say about the process is what the initial state or configuration of the system is. And physically, this corresponds to quenching the system from equilibrium at a very high temperature, in particular infinite temperature, which means that the initial state at time 0 is simply uniformly randomly chosen. Mostly I'll be talking about the case where the initial state is chosen simply by independent fair coin tosses for each site, but sometimes there'll be an extra parameter in which you bias the coins so that there are more pluses than minuses. So I'll begin by talking about the dynamics in the square lattice, and then talk about it on the hexagonal lattice. There are lots of interesting questions about these dynamics that I'm not going to talk about, because I decided to try to discuss things that make some contact with the topic of this conference. So I want to talk about scaling limits of percolation critical points that arise in some natural way in these models, although not independent percolation. So here's taken from I guess a review paper of Bray. Here's some simulations of the coarsening on the square lattice. I think that the first one is not quite time 0. I think it's time 5, but it's close to time 0. The black and white pixels are pluses and minuses, and as you see why it's called coarsening. I mean, the domains grow. All the action takes place at the boundaries, because away from the boundaries, everybody agrees with all their neighbors. So it's only at the boundaries where anything happens. Okay. So, as usual, there are lots of things which are known known to be true but not proven. So there'll be some things I'll state as theorem which may, which are embarrassing because they're so weak compared to what you know is true. So on the square lattice, here's a theorem, not very difficult to prove. Almost surely, with probability 1, every site flips infinitely often. And here I'll be talking only about the symmetric case, where you start with density 1/2 of pluses and of minuses. That statement is true anyway, except for lambda equals 0 or 1, but the other statement, I guess, isn't. That means that if you sit at a particular point, even though, say the origin, even though the domains are growing, the boundaries will move in such a way that they'll keep on passing you by infinitely many times. That in particular would not be the case if you change the dynamics so that when there was a tie, you did not flip. This is the two-dimensional version of a result for one dimension, which was proven quite a long time ago by Aratia. In one dimension, this is precisely the same as the usual voter model, and that model, the motion corresponds to annihilating random walks, and that was the context in which Aratia proved this result. Something not related to what I'm mainly talking about today, but a very interesting open problem is whether or not the corresponding statement is true in more than two dimensions. There's numerical evidence of Stauffer about persistence, which is closely related to this, which strongly suggests that it remains true in 3 dimensions and probably 4 dimensions, but it seems to be quite unclear what the appropriate conjecture is for more than 4 dimensions. Anyway, that's a very interesting problem. It's also true by an argument that extends the one for the square lattice for the triangular lattice that you change infinitely many times. That was done recently by Chris Wu. And it may be, after a conversation this morning, it may be, I'm going to talk about the hexagonal lattice. It may be that the triangular lattice is at least as nice for this model, is at least as nice a lattice to ask analogous questions about as, say, the square lattice. Okay. So I want to talk about percolation properties in this model. So these will be from that point of view, you can think of it, at each time you have a measure describing the pluses or minuses. At time 0, it's independent site percolation on the lattice with density 1/2 or density lambda in general. As time evolves, the distribution of the plus and minuses becomes some kind of dependent percolation model. So it's a sort of one-parameter family of dependent percolation models parameterized by the time. And the basic point I want to make is that it's natural to think of there being a percolation transition at time infinity, as time approaches infinity. So in particular for the square lattice, one can show that for any finite t there is no percolation, namely all clusters are finite, almost surely for t finite. But on the other hand, not surprisingly, looking at the simulation, the sizes of the clusters get large as t goes to infinity. In fact, in the physics literature, it's known precisely how they grow. The diameters should grow like square root of t, but Unfortunately, the status of mathematical proofs is far from that, but we can at least show that the cluster size diverges. Yes, I don't know the answer to that question. In fact, between the time I wrote the first version of my transparencies and this final version, I realized that I had made the stronger statement in the early version, and I decided to be cautious. So let me translate Yuval's, or restate Yuval's question. The statement here is that for any deterministic time, there are no infinite clusters of pluses or minuses. You could ask a more sophisticated question and say, let me first pick the omega in my probability space, and now look as time evolves. Are there any times which may depend upon omega where there might be infinite clusters nevertheless? And I don't think so, but I don't claim to know the answer to that. Actually, the proof. Oh, no, that statement is true in the strong sense. That is, for almost every omega, the size of the cluster at the origin diverges. Yes. Okay, so therefore, as time goes to infinity, it's some kind of percolation, percolation transition. So in the context of this conference, it's sort of natural to ask questions about scaling limits. So I first want to make the point that if you want to talk about a scaling limit, so t equals infinity, or t approaching infinity, is a kind of critical percolation, sort of. What kind of scaling limit should one look for? Well, you don't want to. It doesn't make sense to try to first let t go to infinity and then study a scaling limit in space, because even though it's not rigorously proven, it's clear that the well, you may wonder why I'm saying it's not rigorously proven after the previous statement, but nevertheless, it certainly is. It should be true that the distribution in local regions of the measure describing the configuration at time t should be, in the limit, be supported only on things which are all plus or all minus in any finite regions. That's actually not proven, and that's, although it may look like that, follows from the statement that doesn't, because the statement that the cluster goes to infinity may only be in one direction and not both directions. That's certainly not the case, but it's not ruled out but rigorously. In any case, the point is that the limiting measure at t equals infinity is not an interesting measure because it is presumably simply everything constant. So the scaling limit isn't very interesting. So what you should rather do is take a scaling limit in which you scale both space and time, and one can ask, is there such a limit? I don't know the answer, but John Carty pointed out to me that, like many other things, that has been studied in the physics literature by Bray, and it is apparently believed that the scaling limit is some kind of deterministic Landau-Ginzburg equation, but with random initial data corresponding to the random pluses and minuses at time zero. So I have no reason to doubt that, although there is an aspect of the model which would have led me to think that there would still be some randomness left in the scaling limit dynamics. So that is to say, suppose you have some cluster boundaries looking like this, say with pluses here, plus here, minus here, minus here. So locally, this looks like just a kind of rectangular crossing. Well, the dynamics is such that depending on whether one of these two sites flips or whether one of these two sites flips, you either connect these two clusters or the other way around. And then after a little bit of time, that would tend to be irreversible. And so, so which of the, whether you end up having these two connected and this boundary is moving away or the other way around is somehow intrinsically random, it seems to me. So I would have thought that the scaling limit would still contain some randomness that somehow is related to this phenomenon.
But that wouldn't
But maybe,
some randomness due to the precise condition near the point in the Landau-Ginzburg?
well, the Landau-Ginzburg is a deterministic thing. Maybe, in fact, the right limit is Landau-Ginzburg with precisely this kind of random extra thing put in when you need it. That's just a guess. This is not something I've really studied. Of course, we've been working on the Coarsening model, and this seems to have natural questions that it gives rise to in the context of this.
But you're worried about initial data which would lead to indecision?
No, it's nothing to do with initial data. You have to have things like this because at any finite time, you have a random partition of the space. But that means I would not. Okay, so I guess that, so
there might be some sort of very short-lived stochastic component.
So you're saying that in the scaling limit you would not have anything. You would never have things which were somehow perfectly flat enough to be unsure. Okay. I see. Okay.
I have another question. Why would you expect it to be conform and invariant? You do it.
Yeah. Okay. So.
You do 2 plus 1. So you do 3 dimensions.
Yes. So I first of all, I didn't say I expected it. I asked the question. However, I no longer, after talking with John Carty earlier today, I no longer expect it to be conformally invariant. Nevertheless, it's still an interesting scaling limit to study, but apparently not conformally invariant. What? Let's discuss that privately so I can ask somebody else. But it's it's one of these nonlinear PDEs. It's with a.
Precise dynamics. The dynamics was random or stochastic in the sense that you fixed randomly a spin to be updated? Or?
Yes. So the two random things in dynamics. One is the order in which you update, and the second is when there's a tie and you toss a coin.
Yeah. Oh, yeah, that's
Okay. Oh, I guess I should. I'm not doing this. Okay, let's go to the hexagonal lattice, and let me draw a picture so there's no confusion. In hexagonal lattice, I'm talking about not assigning pluses and minuses to the faces, but to the vertices. So the vertices are pluses and minuses, so not the faces. And so every site on this lattice has 3 neighbors. Okay, that's important. The triangular lattice I mentioned before, in fact, it corresponds to doing it in the faces because every site has 6 neighbors. So notice that on the hexagonal lattice, interpreted in this way, you never get ties, right? There's never a tie between your 3 neighbors because they're an odd number of neighbors. Therefore, it acts just like in the square lattice if you have the conservative rule of not flipping when there's a tie. That is to say, you don't have any flips that correspond to 0 energy change. And as a consequence, just the opposite happens that happened in the square lattice, namely, almost surely every site flips only finally many times. That follows from a much more general theorem, which says that in a very large class of models, including disordered systems, there are only finally many flips that strictly lower the energy at any site. And in a model with an odd number of neighbors, a homogeneous model with an odd number of neighbors, every flip that's allowed at 0 temperature is strictly energy lowering because of no ties. That's the same thing as having no ties. Therefore, there are only finally many flips of any kind. Well, if there are only finally many flips, then there's some limiting configuration. So in that case, one can ask questions about that limiting spin configuration or the distribution that you get on it as a dependent percolation model at time equal infinity. And here's evidence that one should regard that as a critical dependent percolation model of some sort. First of all, the same theorem by the same argument is true for all time, including infinity, that all clusters are finite at any given time, including time infinity. Certainly for small time, the expected cluster size is finite. I would conjecture that it's finite for all t less infinity, but that's not proven. But there is a proof that the expected cluster size at time equals infinity is infinite. So in that sense, at least, it's a critical percolation model, some kind of dependent percolation model. And I'll discuss.
Estimates of the exponent.
Yes, I'm going to talk about that, although it should be taken, when I get to it, if I don't remember then, I should say now that it should be all taken with a grain of salt for several reasons that I'll get into. So this theorem suggests that the time going to infinity corresponds to a percolation transition in which in the limit you get a critical percolation model. But in this case, not only do you not have to do space-time scaling, but you probably don't want to. And here it makes sense to simply talk about, ask questions about spatial scaling limits for the model at t equals infinity. And of course, one can ask all the same questions there. Is there a spatial scaling limit of that dependent percolation model? And I guess one could again ask whether it's conformally invariant. In that case, in neither case was there any evidence that it should be conformally invariant. In the first case, there are reasonable arguments that it should not be. In this case, I don't think there's anything one way or the other at the moment. Although that, of course, could be studied numerically, but hasn't been done yet as far as I know. So I want to talk a little bit about the numerical studies, which also respond to Jennifer's question. So I want to say that the numerical evidence, although it's extremely preliminary, suggests at the moment that two things. First of all, that it really gives more evidence that it does correspond to a critical percolation model, besides the fact that the expected cluster size is infinite. And secondly, that it's an interesting percolation model. But I'll explain why they should be taken with grains of salt. So first of all, what was studied numerically was the following. Now let's go. Remember, there was a parameter lambda, which I mostly haven't used, which was the bias in the initial state. So you choose sites plus with probability lambda and minus with probability 1 minus lambda. And mostly we talk about lambda equals a half, but you can consider any lambda. And for any lambda, you still converge. You still have still the case that every site flips only finitely many times. So you have a limiting spin configuration. Therefore, you have a measure on the limiting spin configurations. And now you're still left with the parameter lambda. So you can regard that as a one-parameter family of dependent percolation models, depending on lambda, which is the bias parameter. But it's the bias parameter at time 0. So the numerical. So look at, say, percolation of plus clusters and how that depends upon the. Look at percolation of. Say plus clusters and see how it depends on the parameter lambda. When lambda is small, you have very few pluses, and you will not have any percolation of pluses. You rigorously at lambda equals 1/2, the expected cluster size of the plus clusters, like for the minus clusters, is infinite. And the numerical evidence is that it's exactly at 1/2 that the expected cluster size diverges. So that as you vary lambda, this thing, besides looking like a critical point as you approach in time, also looks like it's a critical point as you approach in lambda at t equals infinity. So that's more evidence that it should be thought of as a critical percolation model. Now, so here's some. So the preliminary here, the underlining, the two underlines. Those are 2 grains of salt. The first is that the numerical results and data analysis has to be improved, which is why we're recruiting Alan Sokol into the collaboration. But besides that, yes. But he hasn't been involved. It hasn't been involved very long, so he shouldn't be blamed for any mistaken claims I make. So we studied numerically the two critical exponents by use of kind of naive finite size scaling analysis.
Chuck, this is at t equals infinity.
This is
varying lambda.
yes.
And you haven't tried the other one yet to see whether
Yes.
there's crossover.
Yes, that's correct. Well, you could vary t for lambda equals 1/2.
You could hold lambda fixed at 1/2 and then
But the preliminary evidence is that the exponents that you get from finite size scaling, which in the usual, which are the gamma and nu, if you treat it as though it were like an ordinary percolation point, seem not to be their ordinary two-dimensional independent percolation values, which are, if I have it right, and everybody here can correct me, 43/18 and 4/3. However, although, well, here's a comment that 4/3, it's actually the numerical value seems quite close to 4/3, so I'm a little nervous about that, but it doesn't seem to be so close to 43/18. But anyway, all the data analysis is preliminary. So, but there's another point that Giancarlo made to me earlier, which is the second grain of salt, which is that perhaps one should not treat the lambda just like P in the independent model, since lambda was the kind of parameter at time 0, and now maybe you should, for example, be replaced by the plus density at t equals infinity, which is some function of lambda that we haven't really studied, or something else. So that's the second. Any case, this does seem to be a sort of natural dependent critical percolation model. So certainly, spatial scaling limit is in principle of interest, and I have no idea whatsoever whether one should guess that it's conformal invariant, but that is something which in principle could be studied numerically, but hasn't yet. Thank you.
Maybe since we have P, we will defer the questions to a private session.
Why is the following a rigorous proof? If you have a loop of